And the next presentation is by Landon, who will continue and probably finish the story of pure electronic degrees of freedom. And he will also tell about interface, about two different materials, but from slightly different aspects.
So I did my project on simulating the effect of interfacial bonding on electron hole recombination rates in lead halide perovskite-based solar cells. So the basics of how a solar cell work is you shine your light down on it, and normally it's just an n-doped silicon wafer and a p-doped silicon wafer. So the p-doped one, when the light strikes an electron, it'll excite the electron up into the conduction band through this band gap. That's what makes it a semiconductor, I guess, is that there's a small gap here. So once the electron is promoted to the conduction band, it's no longer bound to any particular atom, so then it can move around freely. And at that point, it can move into the n-type silicon and push current through whatever circuit you connect to your solar cell. If an electron and a hole meet, though, then they're going to recombine, and you're not going to end up getting any current out of there, so that is something that needs to be considered when you're designing solar cells. This is basically a schematic of the solar cells that I was trying to produce. I did finally get one of them to work out this way. I guess this isn't really terribly important to what I'm talking about right now. Okay, so these are both the through space model, and these are the through bond model. And basically the differences between the perovskite and the dye, they're either connected through space or they're connected through a methoxy linker group. That's what this little well is right here. And of course that figure is blocked. So basically that would just correspond to there actually being a connection right here on this diagram.
Can you explain what are those things that are connected or not connected?
This is lead halide perovskite. Actually, this might be a picture of a cesium perovskite, just a perovskite either way. And this is the spiro-OMETAD dye. So then, at low momentum, when you start with the electron over here and try to send it across the barrier, you'll see that most of it ends up reflecting back. You really get what's going on. Okay, there we go. So nothing really crosses this boundary. And now I'm going to run these ones, I guess.
The one on the far left is off. Yeah. Not that one. No, one more to the left.
Well,
go all the way to the. One more left. Yeah, that one. Okay.
oh. Okay, so if we start the electron with a higher moment. Okay, so if you start it with a higher momentum, you can see that the wave packet actually transfers through this boundary. But an unfortunate side effect of the periodic boundary conditions that this simulation was running on is that you do have a significant amount of transfer happening across these boundaries, which is an unphysical artifact, and that needs to be accounted for when interpreting the data. So these are graphs that describe the probability of finding the electron either in the dye or in the perovskite. So the solid blue curve here is the one that we're interested in. This tells you the probability of finding the electron in the perovskite. So basically, after all of this stuff here, you're getting a lot of transfer happening through the periodic boundary conditions. So you don't necessarily want to be considering this data back here. So what we're looking at is just the initial, the early times when this is the only major transfer happening right there. So you zoom into these graphs, you just look at this section here and this section here, and you figure out the slope of this linear region to figure out the rate at which the electron is transferring into the perovskite. And you end up getting these transfer rates, which have unphysical temperatures, but you end up getting a very interesting phenomenon where in the Arrhenius plot, it certainly doesn't obey the Arrhenius equation, because if it did, then the Arrhenius plot would appear to be linear. Instead, it appears that the transfer rate is just linear with, it's directly proportional to the temperature of the system. And that is
Okay, let's thank Landon.